Hello and welcome to Power Electronics with Dr. K. I'm going to do a video. I haven't done one in quite a while, but I want to do a video on how to model an idealized diode in LTspice, and let's talk about why we might want to do this. Okay, so here is our overview. Again, we're going to discuss the why and possibly when to use an idealized diode model. We'll talk about the dot model statement for diode, and I'm going to use LTspice as our example. We're going to talk about how we can obtain model parameters from the datasheet. I'm going to do an example. I'm going to use a silicon carbide Schottky diode for our example and show you exactly how you can get from the datasheet the model parameters to put in our idealized diode model. And then I'm going to show you how you can verify the operation of your diode model using a simple a test circuit in LTspice. So let's get started with that. Here's some references, and I'll put these also down below in the description. All right, so when and why would we want to use that idealized diode model? Sometimes you just have a very simple rectifier. It's operating at 60 hertz. It's just a full wave bridge, for example, and there's no real need to use an overly complicated diode model for that. And yet you might be at power circuits that have a voltage drop that is greater than the default 0.7 volts. And so that might be one application where this makes sense. The application that I typically come across is some of our switching power supplies use Schottky or silicon carbide Schottky diodes. And those type of diodes have an extremely low switching loss. It's nearly zero because there really is no reverse recovery time with a Schottky or silicon carbide Schottky diode. If you're using a silicon fast recovery, this might not be the way to go about modeling this. But again, for Schottky diodes, this makes good sense. And you know, many of the manufacturers, if you go on their lines, they're going to provide you a diode model, but oftentimes, not always, but oftentimes that diode model is based off of the Berkeley Spice model, and it's a very elaborate model, and so therefore it does not simulate as quickly as this idealized diode. And so the idealized diode enables a faster simulation for more complex circuits. So those are some of the times you'd want to use this. Let's talk a little bit about this. In an LTspice, we've got two types of diode models, and one of them is a piecewise linear model, and that's the one we're going to use. That's the ideal one, and it fits the conduction regions for the diode. And the other one, and I'm not going to talk about this one, but it is the standard Berkeley Spice model that was developed many years ago. So again, LTspice has two different ones. We're gonna focus on the idealized one. In the idealized one, the minute you put down a forward voltage in the model statement, and I'll show you how to do that, it's going to generate and pick the idealized linear conduction model. There's a number of statements, if you look in the LTspice help files, that you want to specify. There's the reverse voltage breakdown, the forward threshold voltage, the dynamic forward resistance when it's conducting. There's a term epsilon, and that term is to help smooth the knee at conduction. There is the dynamic resistance when it's not conducting, R off. There is the reverse breakdown dynamic resistance when we hit that reverse breakdown region. There is a forward current limit. There is a reverse current limit, and there's also an epsilon term for the reverse knee. So let's just look at a simplified diode model where we have on the horizontal axis our forward voltage. So if I put our diode up here, this would be plus to minus VF, and then we have our diode current, which would be again anode to cathode. When we look at this point here is our V, FWD, that is our forward voltage. It's the knee at which it starts to conduct. We have our reverse breakdown. So there's our reverse voltage there. This slope, which is delta I over delta V, is equal to 1 over the on resistance. So it is the inverse of our on resistance. This slope, again, is 1 over the off resistance. So the slope in this region right here is 1 over the off resistance. This term up here is our forward current limit. This term down here is our reverse current limit in the model card. And this slope is 1 over our reverse resistance when we are in breakdown. So that dynamic resistance is represented by that slope. If you do not specify this in the model card, it will revert to R on, and so those slopes will be the same. The epsilon in the forward controls the smoothness of this knee. It does a quadratic fit. And I'm going to show you, in the model example I'm going to use an epsilon of 0.1, and that actually works pretty well for my model. The reverse epsilon, again, is going to model this knee in the reverse direction on how smooth you want to make that. So those are where the model parameters fit in. Now let's look at how we can get that off of a data sheet. So in this example, I am using a silicon carbide Schottky barrier diode from Rohm. It has a 650 volt reverse voltage on it, forward current of 10 amps. But if you dig down into the data sheet, you will find in the diode data sheets the voltage current relationship when it is in the forward conducting region. And so one of the things I want to look at, and I'm going to use, it's going to be a little bit more conservative, I'm going to use the line for a junction temperature of 125 degrees C. That again is a little bit more conservative, and that's this line right here. I'm going to pick off 2 points. Here's one point that's at 12 amps, and at 12 amps our forward voltage drop when conducting is 1.5 volts. Then I'm going to also look at this point right here. That's 10 amps for that line. And that has a forward conduction of 1.4 volts. Based on those 2 points, we can find R on. And so our R on is going to be 1.5 volts minus 1.4 volts all over 12 amps minus 10 amps. And if you do the math on that, that should give us an R on of 50 milliohms. Okay? So we've got our R on. I'm not going to worry too much about R off on this. I am going to now look, though, at where do we start conducting. And if I follow this graph all the way down, right about here in the graph is where that knee starts. And so that is, I'm going to estimate a forward voltage of about 0.85 volts where that knee starts. And it might be a little bit more, it might be a little bit less, but we'll see how well I do on this estimation. And again, I'm going to use an epsilon on this one equal to 0.1. And so those are the key parameter models. Let me also say, I'm going to put this in. The application I was using, I wasn't going to come close to this, but I'm still going to put it in at 650 volts. Again, that's our reverse voltage off the data sheet. So we have some key parameters off the diode data sheet that I'm modeling. And now I can put those into SPICE. Here is and then here's also my test fixture for SPICE. Notice our forward voltage is 0.85. Again, that's off the data sheet. R on, which is what I computed on the slope of the graph, is 0.05. I'm using an epsilon of 0.1, and I have a reverse of 650. You can put the additional parameters in if you wanted to for I limit and I reverse limit and R off, but for what I'm doing, I didn't necessarily need those. Now the other thing to do is once you create that model, and the way you do it in SPICE is .model. You have your device name, and I'm using D_SCS310AG, which was the Rohm part number. I put in a model in there, and then I changed it to that name, and so it will look up in here. I did not use a Schottky symbol for this one. I just used a regular model. one of the ways we can test this is by putting in a voltage source and putting in a pulsed voltage source where we are going to go up to 1.5 volts. We're going to do it in 1.5 seconds with a period of 1.5. And what that's going to do is create an input voltage that ramps up to 1.5 volts in 1.5 seconds. And so it has a slope of 1. By doing that, we're going to be able to look at our horizontal axis, which will be in time, but that will be representative of our voltage plus to minus across our diode. Transient time, again, of 1.5. So if your data sheet is 2 volts, goes up to 2 volts, then take 2 volts. So go whatever your data sheet is going to tell you, and you can put those parameters in. Now here's the results of the analysis. I plotted the current through the diode. And again, it's as a function of time, but this time represents our actual voltage across the diode. And so we can look at a couple key points. 1.5 seconds is actually going to be 1.5 volts. And notice we're at 12 amps. And again, if I come up to our graph from our data sheet, that was 12 amps. At 1.4 seconds, we're at 10 amps. And again, that's this point on our data sheet. And then we come down to at 4 amps. Let me check 4 amps. We are at 1.1 volt. So if I come across, that is a pretty darn good estimation. And we've got an E here. And again, if we want to make it more accurate, we can modify epsilon for that. Looks like our LTspice model is verified for the device that I have picked. Let's just kind of wrap up with some of the key points. Number one, the simplified diode model is relatively easy to create from the vendor datasheet. Just take the IV characteristics of the diode and do some simple math on the slope of the current and the voltage, and look at where the forward voltage starts to break, and you've got your model parameters. The simplified diode model, in my opinion, is best used for either the general purpose bridge rectifiers or the Schottky barrier diodes where your reverse recovery losses are negligible. So that's probably where you want to use this. And then finally, I always recommend build a simple test fixture like I did here and verify your diode model, and then tune it as needed to fit that vendor's data sheet. Hope that helps you with building up some simplified diode models in LTspice. Thanks for watching and have a great day.